Hello learners, welcome to my YouTube channel Learn with Swagat. Today's discussion is on operating system. But before getting into the lecture, if you are new to this channel, please do subscribe and hit the bell icon to receive the notifications regarding latest videos. So let's start today's topic. Hello learners, today's topic is CPU scheduling. So CPU scheduling is nothing but picking up one of the process from the ready queue and put it into the CPU, because many processes might be waiting in the ready queue to be executed by the CPU. So the program which select one of the process from the ready queue and give it to the CPU is called CPU scheduler, or also called a short-term scheduler. There are different reasons for which CPU scheduling might take place. So let us see what are those. So these are the four reasons, that is when a process terminates, or when a process jumps from running state to waiting state, or running state to ready state, or waiting state to ready state. So let us see it with the help of the process state diagram. So if we see the process state diagram, it will look like this. There will be a new state, be ready, then running state, waiting state. When a process gets created and it will be ready for execution, it will become from new state to ready state. Then if the CPU is free, then it will be going from it will change its state from ready to running. That means it will be actually executing inside the CPU. Okay, and finally when it finishes its running time, means it gets executed, then it finally goes to terminate state. But in between, when it gets executed within the CPU, at that time it might require some resource, or it might need a IO operation. So in that case, it will be jumped to a waiting state. So upon IO request, okay, and finally when IO request get completed, it again jumps back to ready, and from ready it goes to running. IO completion. So our scheduling is this line. That means the scheduler pick one of the process from the ready queue, because in the ready queue many processes might be waiting. So it is the CPU scheduler who choose one of the process from this ready state and put it into the CPU for their execution. So we can write here schedule the process. So similarly, sometime in a time shared systems, we might give some times for each of the processes, and whenever the time for that particular process is finished, we can take out it from the CPU and give it to the ready queue. Okay, that is called time quantum. So now let's see the first thing. So when CPU scheduling decision may takes place when a process terminates, it means, suppose you have a process which is currently running in the system, that means inside the CPU, and finally it terminates. Then at that time, obviously, as because CPU is free, so obviously you have to choose one of the process which are there in the ready state and pick one of the process and give it to the CPU. So when process terminates, obviously you have to invoke CPU scheduler, which will choose one of the process and give it to the CPU. Then second reason is, whenever a process jumps from running state to waiting state. For example, suppose a process is running currently, a P1 process is currently running inside the CPU and it is in the running state. Now during its execution, it requires a IO operation, or it might request for some resource which is not currently available. So at that time, as we know that P1 state of P1 will be waiting. That means it goes and wait here. Here it will wait. Okay. So whenever it will wait here, for example, P1 is now waiting. Now CPU is free. So now, as because CPU is free, obviously CPU scheduler select one of the process again and give it to the CPU. So therefore, whenever there is a process which is running and because of some IO request it jumps to waiting state, then as CPU is free, so CPU scheduler select one of the process from the ready state which are there in the ready states, and then it schedule to the CPU. Okay, whenever I am saying that ready queue, waiting queue, so in every state, to keep track how many processes are in a particular state, every state maintain a queue. Every state in the sense this ready state, new state, and specifically this waiting state. So if there are n processes in the ready state, that means it is represented using a queue. That means within that queue, that queue we say it is a ready queue. So within that ready queue we have n number of processes. Similarly, if m number of processes are waiting, that means the waiting queue contains those m processes which are in the waiting state. Okay, so these two are clear. Now next is running state to ready state. So let's see how this running state to ready state, if a process jumps, then how the CPU scheduling is involved. So for example, this basically happens in a time shared system where we fixed some time for every processes. For example, we decide, let's say there are 10 processes, P1, P2 up to P10, P9, sorry, P10. 10 processes are there, and we fixed that every process must run for 2 seconds. Let's say now when P1 is running currently and the queue is like this, so when P1 goes to the CPU and it is in the running state, after 2 seconds it will be come out from the CPU and next process would go on. So this is where the CPU scheduling again will be helpful, because after 2 seconds when we take out the P1, because we have fixed that P1 will be run for 2 seconds only. So after execution of that time which we have allocated for P1, which is called as time quantum, that means time quantum here is 2 seconds. So when this time quantum expire, P1 has to be moved out of the CPU and put it in the again ready queue, and the next process from the ready queue will be jumped to the CPU, because CPU by that time CPU will be free, because P1 is already taken out by the operating system from the CPU to ready state. So therefore again it is the scheduler who selects again out of that processes which are still there in the ready queue, which process should be going into the CPU. So for running state to ready state, there also CPU scheduling is involved. Now last one is waiting state to ready state. Here, in which case, let's see in which case this will happen, waiting state to ready state. Let's take an example. Suppose some process is running inside the CPU, say P1 is running, it is a high priority process, some priority, okay, not necessarily high priority. So let's say its priority is 10. Now let's say a process which was waiting in the waiting queue is now completed its IO. Means maybe some process, let's say P2 was running previously, and it was because of some IO request, it was waiting in the waiting queue, and during that time P1 is running inside the CPU. Now when P1 is running inside the CPU, let's say during that time P2 has completed its IO. As because it's completed its IO, it will be going to the ready queue. So previously P2 was waiting, now P1, as because P2 has completed its IO, so it will be again added in the ready queue. Now if P2 has high priority than the currently running process, then what will happen is CPU will take out the low priority process which was currently running in the CPU, because a high priority process has already came into the ready queue, that is P2. Suppose P2 priority is say 12. So now it is the time where P2 has to be scheduled into the CPU. Whenever a process going from waiting state to ready state, then also there is a need of involving the CPU schedulers. But it is not always the case, because it is not like if P2 every time whenever a process will be going from waiting state to ready state, then CPU scheduler has to be involved, because it might so happen that whenever if P2, in this case, if P2 is coming from waiting state to ready state and P2 priority is 6, but currently running process is P1 whose priority is 10. So as because a high priority process is already running, and P2 which recently came to the ready queue, which has low priority as compared to the process which is currently running inside the CPU, so there is no need of taking out the high priority process from the CPU. So therefore at that time CPU scheduler will not be invoked. Okay, so therefore this is a probable reason for which CPU scheduler might be invoked, but not in all the cases. But whenever a process terminates, there is no other choice, you have to invoke the CPU scheduler. Similarly, whenever a process going from running state to ready state, when it is going, whenever the time quantum expire, so obviously if time quantum expire, you have to pull out from the process from the running state and put it into the ready state. So that means CPU is free, so obviously you have to invoke the CPU scheduler, and it will select one of the process from the ready queue and put it back to the CPU. And similarly, if some process is currently running in the CPU and suddenly it goes to waiting state, now CPU becomes free. So our always intention should be how we will make the CPU busy as much as possible. So we should not make the CPU idle in any case. Okay, so these are the 4 reasons for which CPU scheduler might be involved. Now as I said, there are different type of queues involved in different states in this state diagram. So let's see what are those. As I already told you that one is waiting queue, ready queue, and for new job, when new jobs gets created, for that we have another queue. So it can be pictorially represented like this. So this is a ready queue, this is the IO waiting queue, this is the job queue when job gets created. So basically from the job queue, one by one process, once they are ready, they jumps to ready queue, and from the ready queue it will be dispatched to the CPU. That means here we have the work of the scheduler, that is called short-term scheduler. Okay, so this part will be done by short-term scheduler. It will select one of the process from the ready queue and put it to the CPU for its execution. Okay, now if you compare this with this one, then you can see that this job queue is this one, IO waiting queue. Then here we maintain the ready queue, and this is where we are, when we say a process is running, is in the running state, that means it is currently running inside the CPU. Okay, fine. Now there are different implementation of the queue which has been implemented inside the operating system, and basically the queues are, if you say this ready queue and waiting queue, these are implemented in terms of linked list. So these are the PCB, process control block of some processes. Okay, and there is a queue header, and rear will point to this end, and front will point to this end. So whenever the process is going from ready state to running state, that means it is the front process always which will be first processed, because it's the front end. Okay, it will be maintained in a queue data structure, but the implementation is using linked list. Okay, similarly this is also the waiting queue. So these are the two terms which are involved in a CPU scheduling context. So one is dispatcher and the latency related to it. So dispatcher is nothing but it gives control of the CPU to the process selected by the short-term scheduler. So it involves switching context, switching to the user mode, and start of the process. These three we will discuss in detail again. And the latency is nothing but the time taken by the dispatcher to stop one process and start another process. So for today we'll finish this, and in the next class we'll be going to discuss about different types of scheduling algorithms and what are their criteria for selecting different scheduling algorithms. Thank you. Thank you for watching this video. If you like this video, don't forget to hit the like button and share with your friends.